In the last video, I started the design of a pass-through bolt with a compression fitting to be 3D printed. In this video, I'll complete the design and use Prusa Slicer to verify the correctness. If you haven't watched part 1 yet, I urge you to go watch that now and then come back for part 2. The next step is the extension. The extension is a threaded part that screws into the head of the pass-through bolt and provides a thread for an end cap to seal the box when the filament isn't being used. It looks tempting to simply build it into the pass-through bolt rather than having it screw in separately, but I made it a separate part for the purpose of printability. By making it a separate part, I avoided having the outer rim of the bolt head and the knurls being a 90-degree overhang. Certainly it would be possible to flare upward from the thread into the bolt head to avoid that, but it would take up a little more space and really wasn't aesthetically what I was looking for. Since the extension really is just a threaded rod with a hole in it, and the thread of the pass-through bolt is really the same thing, I'm going to take a shortcut here. Open up the pass-through bolt in the model tree and find the thread inside. Remember, it's a sweep. Select it and create a draft clone. You'll notice the clone is in exactly the same position as the thread itself, even though unlike the thread of the pass-through bolt, it is not attached to the head. That's just because the clone tool copies the current position of the thing that's being cloned. But since the clone is its own object, we can move it. Select it and go into the data pane. You can see the position matches the sweep in the bolt, but there's no attachment section, so the position can be edited. Set position.z to 0 in order to set it down on the XY plane. Since we have a tool made for cutting out the through hole, we can reuse it. Locate the through hole extrusion in the bolt. Now select the clone, select the through hole, and cut. So we already have most of the part practically for free. All we need to do is chamfer the top and bottom a little bit to make assembly a little easier. But because this is a thread, we can't just use the chamfer tool and call it a day. Select the barrel of the threads and create a sketch. Even though the surface is not planar, when I turn on the cross-section view in the sketcher, we can see that it's done the right thing. An advantage to attaching the sketch in this way instead of just creating it on the XZ plane is that the origin moves to the center of mass of the threaded rod. This will come in handy in a moment for keeping things symmetrical. Select the polyline tool and draw a rough trapezoid with its base on the vertical axis. Select the two opposing points on the smaller length of the trapezoid and the horizontal axis and click the symmetry constraint. Now I'm going to bring the line in a little bit. We don't need perfect dimensions and placement here. We just want to ease the top and bottom a little bit to make things fit together. That looks pretty good. I thought about adding a few more constraints, but honestly that's close enough, so I'll just close the sketch now. Next, select the sketch in the Revolve tool. Revolve it 360 degrees and make it a solid. Select the cut and select the revolve and the Boolean intersection or common. That looks like a good shape. One last bit, it's a little hard to screw a bare thread into a threaded hole, especially if there's some adhesive on the thread to join it permanently. So I'll put a slot in the bottom that will fit a large screwdriver. Select the bottom face of the thread and create a new sketch with the plane face attachment mode. Now draw a rectangle that cuts completely across the extension. Make the slot 1.5 millimeters wide. Now select 2 points on one side and the vertical axis and make them symmetrical. There's no need to constrain the length since the only requirement is long enough. Close the sketch. Make sure it's selected and create an extrusion. We want the slot 2 millimeters deep. It's extruded in the wrong direction, so select the extrude in the data pane and set reverse to true. Now select the common and select the extrusion in Boolean cut. That's our slot. I'll rename that cut to extension, and that's one more piece done. Almost done. Now we just need the end cap and compression nut. Those two are almost identical parts, except that the compression nut has a hole in it for the PTFE tube to pass through, and the cap is solid on the end. Create a new sketch on the XY plane and place a circle at the origin. Set the diameter to 12.5 millimeters. This will make it big enough to have a 1 millimeter thick wall all the way around and screw into the M10.5 thread. Close the sketch and extrude to 10 millimeters. On second thought, I think maybe 8 millimeters would be better. So go into the data pane and change the length forward to 8 millimeters. Once again, we're going to avoid reinventing the wheel. Open up the pass-through bolt and search through it for the sweep used to cut threads for the hole in the head. Select and clone it. We want to clone because we're going to reposition it. Select the clone and go into the data pane, placement.position.z, and set it to 1 millimeter. Hide the extension and hover over the clone to see that it is positioned the way we want. Since the extrusion is on the XY plane and we moved the thread tap up by 1 millimeter, that gives us a 1 millimeter thick bottom to the end cap. Select the extrusion and the clone of the tap and cut. This does not look right at all. I'm not even sure how this could happen. Everything seems to be positioned correctly. There's our answer. When I was looking for the right thing to clone, I made the thread tap visible. So I hide that and I hide the clone, and now everything looks right. These things happen sometimes. Maybe more coffee is called for. I'm not quite through reusing things yet. Select the cut that we just made. Go up into the pass-through bolts and select the through-hole tool and cut. That should do the job for the compression nut. It may be that after a test fitting we'll want the hole to be a little smaller. In that case we could just use a sketch with a circle and an extrude to take care of that. But this is a good first pass. I'll rename this cut to compression nut so we don't get confused later. I'm going to open the compression nut and select the previous cut without the hole and make a draft clone. Rename the clone to end cap. Just to see clearly how everything lines up, I'll move the pieces into place now. The extension needs to move downward. Right-click and select Transform and get it roughly into position. Hover over the extension to highlight it and see that it needs to move down a bit more. Select the extension. Z is negative 6.5 millimeters. Change it to negative 7 millimeters. That should be about right. The compression nut needs to move upward and be rotated at 180 degrees. Looking through the hole, that looks decently close. Now I just need to translate the end cap downward. One final fit test, I'll hover and highlight each piece just to see how it all fits together. That's looking good. So now to get a good overview. Select all of the final parts except for the compression washer. Go to the View pane and set Transparency to 40. This gives us effectively an X-ray of the entire design. I find that sometimes when in the middle of a design, the semi-transparent view can be very helpful. In other cases, it's actually a hindrance. But it's easy enough to turn it on and off as needed. It's almost always helpful at the end as an overview. One final thing for the design. The thread profile workbench by default uses standard clearances. Those clearances are specified assuming metal nuts and bolts being cut with a tap and die or similar process. FTM printed plastic is simply a different medium, and that's not nearly enough clearance for it to work. Occasionally you might get lucky, but more than likely it's just not going to fit together. Going back to what I said at the beginning, one advantage of the thread profile workbench is that things can be customized. We can leave the external threads alone, they should be just fine. But the internal threads are going to need to be eased. Start with the thread that created the hole in the head of the pass-through bolt and select the V-thread profile. In the data pane, go to the minor diameter. Currently, the minor diameter is 8.38 millimeters. Increase that to 8.58 millimeters. That will cause it to cut the grooves just a little bit deeper and allow a little bit more clearance for the external threads to mate cleanly. Fortunately, unlike changing the height, changing the minor diameter of the thread just works. One big advantage of all of the reuse we did earlier is that changing the thread in just one place has also fixed the clearance for the threads in the compression nut, the end cap, and the retaining nut. Now that we have our design, it's time to slice it for 3D printing. I know that some of you are just here to see the design and aren't really interested in the 3D printing, but in this case you really should stay tuned because the slicing reveals a problem that was very hard to see otherwise. For that reason, it's sometimes useful to run a design through a slicer such as Prusa Slicer, even if you never intend to 3D print the part. First, I need to select all of the final parts in the design. Now go to the File Export, and in the dialog, export this to passthrough.step. Now go to Prusa Slicer. Add object and select passthrough.step that was just exported from FreeCAD. For some reason, Prusa Slicer finds this step file to be somewhat complex, and so it takes what seems to be an unreasonable amount of time to do the import. In this case, about 1 minute and 30 seconds, in spite of running on a Ryzen 3900X processor with 24 threads available. To be fair, it isn't just loading the file, it's also converting the individual parts to a mesh as it goes. That does take a bit of computation. The import is done and it looks pretty decent. I'm running with my modified version of the Prusa Slicer and I still have the anti-gravity turned on. So it brings the part in exactly as it's positioned on the XY plane in FreeCAD. That is, with the extension and the end cap below the bed. This will be easily fixed up later. If you're running the standard Prusa Slicer, it will have automatically raised the object up to rest on the bed. Because we brought this in as a single step file, all of the parts of it are grouped together as a single object called pass-through. The first thing we need to do is right-click on pass-through and go to Split to Objects. This breaks it all apart into our individual pieces to be printed. One thing that looks a little bit suspicious here is that we have pass-through 1 and pass-through 2 as separate objects. This requires investigation. Go to the sliced view and hide away pass-through 1 so we can get a look at pass-through 2. That looks suspiciously like the sacrificial disc added to make the slicing go easier. The circular perimeter around it tells us that it did not get fused into the bolt as expected. Make pass-through 1 visible again and move down through the layers until we expose pass-through 2. Zooming in just a little bit, the problem becomes clear. The sacrificial layer was extruded in the wrong direction. So instead of becoming part of the bridge, it's actually 1 layer below it, hanging there in space in a perfectly unprintable way. No wonder we got so many warnings. But no worries, we just need to go back into FreeCAD, reverse the direction of the extrusion, and do our export again. Look through the pass-through bolt until we find the sacrificial layer. Select it and in the data pane set reverse to true. This is causing an odd problem. Suddenly the retaining nut is in error and a refresh is not helping. Looking at the pass-through bolt and highlighting the sacrificial layer doesn't seem very informative. So I didn't make the entire exploded slice visible. Now I notice that slice.1 looks suspiciously like what should be the retaining nut, and slice.0 looks like everything else. On reflection, it seems a little weird that slicing apart gave us 3 slices in the first place. I'll delete the retaining nut. I'll right-click slice.1 and select Transform. Move it up to where the retaining nut should be. Rename slice.1 to retaining nut. I'm guessing that the weirdness was because the sacrificial layer was successfully fused but was never contiguous. The part workbench doesn't mind fusing 2 solids that don't touch. If we hadn't run this through the slicer or some other CAM program, that issue might never have become apparent. So with that fixed, it's time to re-export the step and re-import into Prusa Slicer and see how things go this time. Back in Prusa Slicer. Now clear the print bed and do the import again. Again we have an interminable wait while the slicer mulls things over. At long last, here it is. Split pass-through to objects. Looking at the object list, this looks a little bit more promising. We see that pass-through bolt 01 is just a single object this time. Very likely the sacrificial layer has correctly fused. Hide everything with the bolt and go to the sliced view. Moving down to the layer where the bridge should be reveals that indeed the sacrificial layer has fused correctly. And it has produced a nice neat bridge with lines going directly across. This should print fine. Everything's pretty standard from here. Just go through each object, select the face to put on the bed, and slide them around and arrange them so they'll print neatly. I do recommend turning on a brim for this one, particularly since the extension is taller than it is wide and it's tapered at the bottom. Everything nicely arranged and nothing is sinking into the bed. So it's time to either save the G-code or send it directly to the printer. Your choice. As I said previously, I've printed this in PETG with good results. It's worth noting that Prusa Slicer estimates the cost of this print at 12 cents. Of course, if you add in a reasonable hourly rate for design time on a one-off, the economics don't really work out compared to buying from ready-made parts. However, if I bill my time to continuing education, material for making a YouTube video, or just hobbyist fun, the 12-cent filament cost definitely beats buying parts. Thank you for watching. If you liked this video or found it useful, please like, subscribe, and share. If there's anything you'd like to see covered here, please let me know in the comments below.